Okay, so up to now we have discussed about what happens regarding the description of the system, in particular of the total energy of the system due to the contribution of the phonons, and we have seen what is the important contribution that the ionic oscillations give to the specific, to the case of the evaluation of the specific heat of the system. And that was one of the problems that we, let's say, were not able to solve from the beginning of the lessons. So at this point, the introduction of the this additional degree of freedoms for what concerns the ions in the lattice allows us to, again, give a description of this important feature that we observe in the solid state, that is the specific heat dependence on temperature. Another thing that for the moment we have not been able to explain is why the electrons suffer or undergo collisions during their motions within the lattice. As when we solved the Bloch equation, so a result of the Bloch theorem is that the lattice, the static lattice, is not able to, let's say, produce a collision or to act as a source of collisions for what concerns the electrons, because the Bloch states are stable solutions of the Schrödinger problem in the case you consider the full ionic lattice. So the ions by themselves are not able to produce a collision. But what happens when we consider the fact that the ions are not fixed in their positions, but are allowed to oscillate with respect to the equilibrium position? So with respect to the, let's say, static periodic ideal lattice that was used by Bloch when Bloch solved the Schrödinger equation, so the Bloch solution is related to the static lattice. If the lattice displays a distortion due to the fact that you have an oscillation that is propagating through the lattice, this means that the periodicity of the lattice may be destroyed, because you have this deformation of the lattice that somehow alters the periodical structure of the lattice itself. So on average, the lattice is still periodical because you are able to observe the Bragg reflections if you make an X-ray experiment. So on average, the periodicity is still there, but locally you have that this deviation of equilibrium produces a distortion of the lattice structure. So that distortion may interfere with the electronic motion within the lattice. As again, the Bloch solution for the electrons is valid only in the static lattice approximation. So the idea is that this additional degree of freedom for the ions, that is the possibility that their motion is, let's say, close to the equilibrium position, but not, that they may oscillate with respect to the equilibrium position, may be a source of instability for the Bloch wave function, irrespective of the shape of that wave function, whether you find that in the free electron approximation or in the tight binding approach or in another different method, using another different method. So the idea is that the oscillation may interfere with the propagation of the electron through the lattice, as the, let's say, actual periodicity of the lattice changes from point to point depending on the oscillation motion that the ions in a specific region of the lattice are displaying. So the general idea that you may obtain from this picture is that the presence of the oscillations in the lattice may be a source of disturbance for what concerns the electrons. What was just to try to transform this expectation into a calculation, so to try to evaluate if there is or there is not an actual interaction between phonons and electrons, we may use as a starting point for the evaluation the expression for that relates the interaction, sorry, the energy, the interaction energy that may correspond to the interaction between one electron in the system and the ionic lattice. So in that case, you have the interaction between the negative charge of the electron, and we may consider the let's say, if we consider as was done for the Hartree approximation, the interaction between the electronic charge and the electron-ion interaction potential that depends on the actual position of all the ions in the system. Just a comment, just to write in a better way, for me it's easier to reduce slightly the size of the point of the pen here. Is it fine for you now? Are you able to see clearly what I'm writing, or do you prefer that I go back to the previous size of the pen?
I think it's clear like this. We can see it clearly.
Okay, thank you. So this is the general expression. If we consider R was in the static lattice approximation the position of the actual ion in the system, but now the position of the ion is not fixed. So we have to include the fact that we have to replace R using R plus U of R, where U of R is the deviation from equilibrium of the ion that is in position R. So this is the static case. If we consider the dynamic one, then we have d3 of R, the electronic density, and then the summation over R of the electron ion potential, R minus the equilibrium position minus the deviation from equilibrium. So this is the actual interaction term. If we use at this point the same approach that was used for the quadratic approximation, that is, if we try to make a Taylor expansion of the electronic ion interaction potential, then we have that this is minus C, then the integral over the position of the electronic density, then we have the sum over R of the electronic ion interaction potential evaluated, let's say, at the equilibrium, so static situation. Then we have the perturbation. So we have minus C, d3R, the electronic charge density. Then we have the sum over R of the gradient of the electron-ion interaction potential evaluated at the equilibrium times the deviation from equilibrium, due to the fact that the perturbation, the deviation from equilibrium within the parenthesis has a minus sign in front. Then when you make the derivative, this minus sign appears here, and due to that, this minus E is transformed into a plus E. So this plus here is due to the combination of the minus sign of the charge and the minus sign coming out from the derivative of the, when you make the gradient here. So, and in general, one stops here. This is not zero as it happened when we consider the approximation, when we try to make to evaluate the expansion of the ion-ion interaction potential, because in that case, the ion-ion potential the gradient, sorry, was 0 due to the fact that the lattice configuration was the equilibrium one. In this case, we consider the electron-ion interaction potential, so we may not say that the gradient is equal to 0, and then one stops at just at the first order of approximation. So this is the, let's say, term that was handled by the Bloch theorem, because in the case of the Bloch theorem, you actually write down into the Hamiltonian the effect of the electron-ion interaction, and you consider that. So this is just the contribution to the energy coming out from that term is handled by the Bloch theorem approximation. So what we need to evaluate now is the contribution to the energy coming from this term here. The idea is to try to write this term using the second quantization approach. To fulfill this task, we may use the second quantization approach both for the electrons and for the phonons. So if we rewrite this term here in terms of creation and destruction operators, both for electrons and for ions, for phonons, then it's easier to discuss the final result in terms of interaction between electrons and phonons as a combination of processes where you may have a creation or a destruction of an electron, or a creation or a destruction of a phonon. So the idea is the starting point of the when we try to start from the displacement field of the ions and apply the second quantization approach, what we found was that U of R was related to the creation and destruction operators for phonons. So what we saw was that U of R, that initially was set as the summation over K and S of 1 divided by the square root of the number of ions Q Ks polarization vector e to the I K R. So this was the initial expression for U as a function of Q. Then using the change of variables that we used to switch from the, let's say, amplitude of the normal mode oscillation to the creation and destruction operator for phonons, this is equal to sum over K and S 1 divided by the square root of n. Then in place of QKS, we have the creation operator corresponding to minus Ks plus distraction operator corresponding to Ks. Then we have the polarization vector, and we have the phase. So this is the expression of U as a function of creation and destruction operators for phonons. As this expression starts from another expression that is a representation in the Fourier space of the displacement, then what is done is to write all the other terms using the Fourier representation. So also the electron-ion interaction potential may be written in terms of the Fourier transform of that. So this is equal to a sum of 1 divided by the volume sum over P, Vp, so the Fourier transform of the interaction potential corresponding to wave vector P, e to the I P R minus R. And just to, let's say, here, this K, the wave vector K that we have here, is a wave vector that describes a phonon. So the phonons are the wave vectors of the phonon are defined in the first Brillouin zone, and the same will take place for electrons. So we may describe electrons and phonons just using wave vectors belonging to the first Brillouin zone. So due to that, we may just write this as 1 over V and use a sum over P, sorry, just to distinguish, I will call that Q, sum over Q and G, where Q is a vector of the first Brillouin zone, and G is an arbitrary vector belonging to the reciprocal lattice of V Q plus G e to the I Q plus G R minus capital R. So what I've done is just to write P as Q plus G, where Q is a vector of the first Brillouin zone and G is a vector belonging to the reciprocal lattice. So P in general is an arbitrary wave vector. And just to stress the fact that I may use also vectors, mainly vectors belonging to the first Brillouin zone, then one decides to rewrite things in this way. Then at this point, we have an expression for V, an expression for U. We miss an expression for the electronic density. If you remember, when we use the second quantization approach, the operator that represented the electronic density was the density operator So we may use this density operator to represent the electronic density in second quantization, and this operator can be written as sum over k and k prime. In this case, we have the creation operator for wave vector k times e to the minus I k r, and then we have C, the distraction operator for k prime e to the I k prime r. So in this picture, we may combine the two phases. So we have sum over k prime of e to the minus I k minus k prime r. Then we have creation operator for k, distraction operator for k prime. If we call k prime minus, sorry, if we call k minus k prime m, then this transforms into sum over k and m of e to the minus I m r. Then we have creation operator of m plus k, distraction of k. Here you may replace k by m plus k prime, and then you may change the name from k prime to k. So we have at this point this expression for what concerns the density operator expressed using the second quantization approach. So at this point, we may introduce into this expression these three terms to see what happens to this full expression. Now there will be many indexes. I will try to let's say control to do not miss anything, but please help me in checking that I use the right values of the indexes and the calculation is fine. So the full expression is we have the electronic charge in front of that. Then we have 1 divided by the volume due to the Fourier transform of the electron-ion interaction potential. Then we have 1 divided by the square root of n due to the Fourier transform of the u of r when we express that using the second quantization approach. Then we have the integral over d3r. Then we have the electronic, the density operator. So there is a summation over m and k e to the minus I m R. Then we have C cross M plus K, C K. So this is the contribution of the density operator for the electrons. Then we have the summation over, there is a summation over R, and this summation over R was initially there when we considered the interaction between one electron and all the possible ions. Then we have a summation over Q, G, and S that regard the phonon variables. In this case, I'm sorry, when I defined the QKS, I forgot the LKS divided by the square root of 2 factor, and LKS is equal to H bar mass of the ions omega Ks to the power of 1/2. So I forgot that because the actual definition of QKS is LKS divided by the square root of 2 times B cross minus Ks plus BKS. So I forgot this coefficient when defining before the actual expression for creation and destruction operators. So here I have B minus Ks creation plus BKS. So this is the representation of the of QKS. Then there is the polarization vector. Then I have e to the I k, sorry, not small r, but r due to the representation of the deviation from equilibrium using the second quantization approach. Then I have v of q plus g, and this is the representation of the Fourier transform of the potential. Here, within this term, I have not to include the actual potential, but the gradient of that with respect to the position coordinate. When I make the gradient, v is unaffected because v is just a term that depends on the wave vector, not on the position coordinate. There is the phase, and when I make the derivative with respect to the, there is the phase. When I make the derivative with respect to the position coordinate, I have a q plus g. I q plus g. So that comes down when I make the derivative with respect to the position vector. And this, I think that this should be everything. So I have electronic contribution, phonon contribution, electron ion potential contribution. So what is the next step? So I have the E divided by EV square root of n, then I have the integral over d3r. Then in this case, the summation over r, so if I consider the summation over this index, the summation over that index involves this phase and part of this phase. So in this picture, if I consider the, if I make this summation, the summation over r of e to the I k r, then I have e to the I q plus g times minus r. This is equal to n times delta k q plus g. So due to the fact that, again, the R index is found just in this phase and in this phase, I may perform the summation, and due to that, I have an additional n factor up here, and then I have this delta kq plus g. So due to that, I may remove all the k indexes that I have in this summation and just let just one index of summation that is q. So due to that, I have a sum over m that comes from the electrons, a sum over q over g and over s. So I have e to the minus I m r c cross m plus q plus g. Then I have, yeah, c q plus g. Then, okay, L q plus g divided by the square root of 2. Then I have b cross minus q plus g s plus b q plus g s e q plus g s. Then I have the scalar product with this phase factor I q plus g, and then I have v of q plus g. Please consider that is okay. No, maybe just one point, because I do not. Sorry, I'm comparing this just to avoid mistakes. I'm comparing this calculation with the calculation that I have done already before, and this is something that is not fine with this C Q plus G. Yeah, the point is that I should have done this transformation regarding the summation over R before introducing this summation into the integral. I'm sorry for making that. Let's say, if you don't mind, just to avoid the to write everything here. No, maybe it's better that I cancel what I've written here and I start again with the new calculation. So now I cancel this. I'm sorry, I just inverted the order of so this is G. Okay, so I just focus. I'm sorry for this this point. If I just focus on this term and I applied exactly this transformation, then I have that the summation over R disappears, and yeah, the summation over R disappears. So I have a summation over. So I had the K index for the phonons, and sorry, let's say, I was sure everything would have been fine, but okay, I will just, I also try, because I'm afraid that this may produce confusion. I will also remove this part here. So I just focus on the part concerning the phonons.
Professor, so we now focus on that summation, and then we take the integral.
Yeah. I'm sorry,
Okay.
I inverted the order.
No problem.
I should have first checked just this summation. So I have the sum over Q, K, G, and S. And the result of the summation is this delta. So I have this n factor in front of the summation. Then I have L. In principle, I should write Q plus G divided by the square root of 2. Then I have B cross minus Q plus G S plus B Q plus G S E Q plus G S e to the I, sorry, this is not here. Then I have V Q plus G. There is an additional phase over the R coordinate, and then I have I Q plus G. Due to the fact that B, L, E are quantities related to phonons, so they are periodical in the reciprocal space and at the same periodicity of the reciprocal lattice, this is transformed into sum over, who disappears because I have this delta. The K disappears, sorry, due to this delta. So I have a summation over Q, J, G, and S of L of Q divided by the square root of 2, B cross minus Q S plus B of Q S, E of Q S, and then I have the scalar product with I Q plus G, V Q plus G, E to the I Q plus G R. So I may drop the G factor, the G term here due to the periodicity of B and E and L, because L depends on the frequency. So at this point, I may introduce this term into the integral. So what I have here is I have E, then the square root of n, the volume, then this n factor here, the integral over d3r of the ionic electronic contribution, that is a sum over m and k of e to the I m r c cross m plus k ck, and then I have the summation over q, g, and s. This factor here is called g of q g s, just to simplify the expression. So here I have g of q capital G and s. Then I have the B cross minus QS plus BQS, and then the phase. At this point, when I make the integral over the, if I consider this phase and this phase, then while making the integral, was that correct? Yeah, I forgot, sorry, that there was a minus sign here. At this point, this integral, the integration over R gives, so the integration over d3R with e to the minus I m r e to the I q plus g times r gives a volume times a Kronecker delta m q plus g. So at this point, I have a volume, so this volume here disappears. So I have E times the square root of n, and then I have the summation over k, q, and g, and s. So I have C cross q plus g plus k, ck. Then I have this g factor, and just to simplify additionally this expression, please include this square root of n factor within the definition of g. So I have q, g, and s, and then b cross minus q s plus b q s, and this is the final point of the calculation. So about 11, so I will make just a short comment concerning these three terms, and then on Monday morning I will make a more complete comment on what happens here. So we have the opportunity in this case to have two couples of operators. So we have C cross Q plus G plus K, B cross minus Q S, sorry, I forgot, C, K, B minus Q S cross, and then we have C cross Q plus G plus K, CK, B, Q, S. What corresponds to the first operator? First operator, I write those on a separate page, so we have more space. So I have C cross Q plus G plus K, C K, B cross minus Q S, and C cross Q plus G plus K, C K, B cross Q S. If you consider the first one, we have a creation operator for phonons, a distraction operator for electrons, and the creation operator for an electron. So the only thing that exists in the system, sorry, this is BQS. So if we apply those operators, we need to have in the system one electron with wave vector k. So we have the electron with wave vector k. Then we have a creation of a phonon, so a lattice oscillation with momentum minus k and polarization s, and the corresponding creation of a new electron with wave vector q plus g plus k. So the idea of this behind this process is you have an electron in the system. That electron excites a phonon. So due to the motion of the negative charge, you interfere with the motion of the ions. Then what the electron produces in the system is an oscillation of the lattice. This oscillation has a wave vector minus q and polarization s. The electron, due to this interaction, jumps into a new state that is described by the wave vector q plus g plus k. If you notice here, if you sum up the initial wave vector is k, the final wave vector is k plus q plus g minus q. So we have k plus g. So there's not the strict conservation of momentum of the wave vector, but this momentum, the wave vector is conserved apart from the presence of this vector G. And this is something that we have already found when discussing the interactions within the solids within the lattice. The second process is described as by the second combination of operators. Here we destroy both an electron and the phonon. So we have an electron with wave vector k interacting with a lattice oscillation with wave vector q and polarization s. After the interaction, we have a new electron with q plus g plus k. So in this case, an electron is traveling through the ion, absorbs the energy and the wave vector of a phonon, and jumps into a new state that is described by q plus g plus k. Also in this situation, if you notice, the sum of the initial wave vector is k plus q, the final wave vector is k plus q plus g. So no strict conservation of the total wave vector of the system or total momentum of the system, since at the end we're using free electrons, but the momentum is conserved apart from a vector belonging to the reciprocal lattice. So these two processes describe the excitation of a phonon due to the electron lattice interaction, or the absorption of a phonon due to the electron lattice interaction. So we have the opportunity to describe those two processes, and the parameter that is related to the strength of those processes is GQGS. So this term gives us an idea of what is the strength of these kind of interactions when we describe the contents, when we want to sum up the energy coming out from all these kind of interactions to concentrate on the total energy of this electron that is interacting with the phonon system. So at the moment, I'm going to stop here, and on Monday morning I will start from this point, giving some more comments also concerning the final expression for G. Okay, sorry for the delay. I'm slightly in delay with respect to the typical timetable. Do you have comments or questions regarding this part?